Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we'll be looking at Maclaurin series. Now, many functions can be written in the form of an infinite polynomial series. For example, e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Sine x can be written as an infinite series. Cos x can be written as an infinite polynomial series. These infinite series, they can be derived from first principles by using Maclaurin's theorem. What is Maclaurin's theorem? Well, it starts off by assuming that whatever function you're interested in, that it can be written in the form of an infinite polynomial series. So that we can write f of x as some constant plus another constant times x, plus another constant times x squared, and so on. Then we find the differentials of f of x. So the first differential would be that, the second differential would be that, the third differential that, and so on and so on. And in general, the rth differential of x would be 2 times 3 times 4 up to r, which is r factorial, times by ar. We now assume that f of x and all of its derivatives exist at x equals 0. And we calculate all of those values at x equals 0. So that's what we've done so far. Now we substitute in x equals 0 into each of these. So f of 0 will just equal a0. Each time, all of the terms which have got an x in them vanish if x equals 0. So the first differential at 0 will equal a1. The second differential at 0 will equal 2a2. The third differential at 0 will just equal 6a3, and so on. And in general, the rth differential at 0 will equal r factorial times by ar. Now, what we actually want to know are the values of these constants. If we know what a0, a1, a2, and so on are, then we know the infinite series. So we just need to rearrange each of these so that we can find these values of a. So for the first one, that means that a0 will just equal the value of the function at 0. a1 will equal the first differential at 0. Rearranging this gives us a2 is the second differential at 0 divided by 2 factorial. The third one gives us a3 will equal the third differential at 0 divided by 3 factorial, and so on. And in general, ar will equal the rth differential at 0 divided by r factorial. So that's what we've done. What we do now is we substitute each of these values for a into f of x. And that gives us Maclaurin series, which is that f of x is equal to the value of the function at 0 plus the first differential at 0 times x plus the second differential at 0 divided by 2 factorial times x squared, and so on, with the general term being the rth differential at 0 divided by r factorial times by x to the r. Okay, let's have a look at what this means in practice. So using Maclaurin series, have a go at finding the first 4 terms and the general term, the rth term, of the series expansion for f of x is equal to the log of 1 plus x. I'll let you have a go at doing this yourself first. So have a go, pause the video, and come back to me again when you're ready. Okay, let's have a look. So first of all, f of x equals log 1 plus x, that's what we've been given. And if we substitute x equals 0 into that, we'll get f of 0 is equal to the log of 1, which is 0. Differentiating that gives us 1 over 1 plus x. And if I substitute in x equals 0, I'll get the first differential at 0 is equal to 1. The second differential is minus 1 over 1 plus x squared. Substituting in x equals 0 gives me the second differential at 0 is equal to minus 1. The third differential is 2 over 1 plus x cubed. Substituting in x equals 0 gives me the third differential at 0, which is 2. The fourth differential of x will equal minus 3 factorial over 1 plus x to the 4. And if I substitute in x equals 0, I'll get the fourth differential at 0, which is equal to minus 3 factorial. And so on and so on. And the general term will be this. Now, there's 2 parts to this, and we'll look at them separately. First of all, we've got this minus 1 to the power of r plus 1. We get something like that with many of these series where you have a change of sign every term. So it goes from plus to minus to plus to minus. And the sign is going to continue to change every term from then on, because whenever we differentiate, we'll be multiplying by a minus number. So that makes the terms change in sign. Now, the way we show that in a general formula, it's always the same. You have minus 1 to the power of something. If you've got minus 1 to the power of something that goes up by 1 each time, then the sign of that will change from minus to plus to minus to plus. Sometimes this power will need to be r, sometimes it needs to be r plus 1 or r minus 1. You'll need to check what actually works for the series that you're using. In some more complex series, the power itself can be more complex, but you always have minus 1 to the power of something. And looking at the terms, on the top, we've got r minus 1 factorial. On the bottom, we've got 1 plus x to the power of r. And if I substitute x equals 0 into those, I'll get the rth differential at 0, which is minus 1 to the power of r plus 1 times by r minus 1 factorial. And if I substitute all of those into Maclaurin series, then this is what I get. So that's what we've done so far. Now, if you look at these fractions, they've got factorials on the top and factorials on the bottom. Most of the terms cancel each time. And that will give us the log of 1 plus x is equal to x minus a half x squared plus a third x cubed minus a quarter x to the 4, with the general term being minus 1 to the power of r plus 1 times by 1 over r times by x to the r. Now, it is important to note that some infinite series, they work for all values of x. And what we would say is that they are valid for all real values of x, where x is a real number. But not all series are, and this one isn't. So the series for log 1 plus x, it's actually only valid for values of x between minus 1 and plus 1, where it can't equal minus 1, but x could equal plus 1. Now, if you're taking an exam where you're given a formula book in the exam, you should check which of these infinite series with their range of validity are given to you in the formula book, and which, if any, you need to learn yourself. Okay, example 2 is one of the applications of these infinite series, which is to find estimations, to whatever degree of accuracy you want, of specific values of a function. So this time, using the first 4 terms of the series expansion for log 1 plus x, given there, estimate the values, first of all, of the log of 1.01, then log of 1.05, then log of 1.5. In each case, comparing the answers you get with the actual values, work those out with a calculator, and write down to what degree of accuracy these estimates, just using the first 4 terms of the infinite series, to what degree of accuracy they are correct. In the first one, you'll notice we've got the log of 1.01. Writing it in this form means we'll have the log of 1 plus 0.01. So in the first example, x will equal 0.01, and so on from there. Okay, I'll let you have a go at working your way through all of this. So pause the video, have a go at doing this, and then come back to me again when you're ready. Okay, let's have a look. Now, as we said, the log of 1.01, which is what we're asked to estimate in the first question, is the log of 1 plus 0.01, and then it's written in this form. So where x is equal to 0.01. And all we have to do is substitute x equals 0.01 into the series. I only need the first 4 terms for this question, so that is what I would have. And if I put all of that into the calculator, then I'd get 0.0099503308333. And there is a reason why I've written so many numbers in the decimal. And it's because if you work out the exact value of the log of 1.01 using your calculator, then what you get is this. And it's the same as the estimate to a surprising degree of accuracy. Now, the reason for that is these series have powers of x where the power goes up by 1 each time. And x is such a small number. So as we take higher and higher powers of it, it very, very quickly becomes extremely small. And each further term becomes negligible. So in this instance, the estimate, just using the first 4 terms of the series, it's actually accurate to 9 decimal places or 7 significant figures. Now, when we increase the size of x here, the degree of accuracy will go down because these terms will stay slightly larger. So the log of 1.05 is the log of 1 plus 0.05. Substituting in x equals 0.05 into the series would give me that. Throw all that in the calculator and you'll get 0.04879010. Working out the exact value of log 1.05, we get 0.04879001 and then the decimal changes. So slightly less accurate this time. This time the estimate is only accurate to 7 decimal places or 5 significant figures. Now in the third example, we've increased the size of x a lot. It's gone up to 0.5. So we'll have the log of 1 plus 0.5. And if we substitute 0.5 into the first 4 terms, this is what we would get. Put that in the calculator and you get approximately 0.43229. If I work out the exact value of the log of 1.5, then I get this. And because the value of x is so much larger, the degree of accuracy of the estimate has gone down substantially. And in this case, the estimate using the series expansion, the first 4 terms, is only accurate to 1 significant figure or 1 decimal place. Okay, example 3 comes back to the basic application of Maclaurin series to find an infinite series. And in this instance, you're asked to find the first 5 terms of the series expansion for sine x. So using exactly the same method as we used for log 1 plus x, have a go at doing this yourself. Pause the video and come back to me when you're ready. Okay, let's have a look at this. So f of x is sine x, and if I substitute in x equals 0, that'll give me f of 0 equals 0. The first differential will be cos x. If I substitute in 0, I get 1. Second differential is minus sine x. Substitute in 0, I'll get 0. Third differential is minus cos x. Substitute in 0, I get minus 1. The fourth differential is sine x again. I'm back at the beginning. And the fourth differential is 0. And then this pattern will just repeat. So the fifth differential is cos x and so on. Now what that gives me, if I substitute in these values into Maclaurin series, is that sine x is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial and so on. Surprisingly powerful method. You get the series expansion very quickly. And this particular series, as with cos x, it's valid for all real values of x. One thing which is very important to note, which is if you're ever working with a series expansion for a trig function, x must be in radians, not degrees. Now, the general rule is anything that's even vaguely connected to calculus must be using radians if you've got an angle. Radians is always safe to use, degrees is sometimes. If you're in doubt at all and the choice is yours, then I would use radians. Now that matters in this next question. So using the series expansion that we've just done, we're asked to use the previous answer to estimate the value of the sine of 30 degrees. First of all, if we just use the first term, then add on the second term, then add on the third term, then add on the fourth term, just to see how the accuracy increases as we use more terms of the series. But the first important thing is you can't put 30 degrees in for x. You have to change that to radians. Okay, I'll let you have a go at doing all of that. So pause the video, have a go, and come back to me when you're ready. Okay, let's have a look. So the first thing, the most important thing, sine of 30 degrees, then that means that x will equal pi by 6 radians. And it's pi by 6 that we have to substitute into this expansion. Now, one good thing about choosing 30 degrees is we know the sine 30 degrees. It's a half. So with each of these questions, we'll be able to see exactly how close we are to a half. So if I just use the very first term, then sine of x will just equal pi by 6. And pi by 6 is 0.52359, which is surprisingly close to a half already, even when you just have the very first term. If I use two terms of the series, then I'll have pi by 6 minus pi by 6 cubed divided by 3 factorial. And that gives me 0.499674, which again is surprisingly close to a half. If I use the first three terms, then I'll also have pi by 6 to the power of 5 divided by 5 factorial, which gives me 0.5 and then 4 zeros, 2132. And if I use the first four terms of the series, then I add on this term here, and I get a number which is very close to 0.5. And you'll notice it's oscillating either side of 0.5. So it starts just above, then just below, then just above, then just below. And that's because each time we're adding on a term, then taking away, then adding, then taking away. And the reason why it's getting so close to 0.5 so quickly is these factorials on the bottom of the fractions. So these factorials, they get very, very big very quickly, which means that these extra terms get very, very small very quickly as you divide by the factorials. Okay, that gets us to the end of this lesson. If you've got the textbook, then you can turn to pages 127 and 131 and have a go at both exercise 7a and exercise 7b. Thank you very much for listening, and cheerio.